welcome back. So today is our last chapter. We're ready for chapter 8, the origin of the solar system and extrasolar planets. Today's kind of what are we summary is that we are planet walkers. We have evolved to live on this beautiful planet, Mother Earth, and if astronomy has taught you anything so far, it should be that astronomy is about you. What are we? And so we do live on a planet. We are planet walkers. And this planet whirls around our star, the sun, which is, kind of out of stardust, right? We are stardust. And this star moves throughout the family of stars, very endearing, the family of stars that is within our parent galaxy, the Milky Way galaxy, which is just one galaxy of a universe filled with galaxies. And so even though we are very small, we are very much a part of this universe. And so the universe is about you. The study of astronomy is about you. So hopefully you're getting that take-home message by now that we're towards the end here. And so it is all around us, and so hopefully you have begun to kind of explore your universe, of which you are very much a part of this very large and very beautiful universe. Okay, so chapter 8, we're going to continue on. So in 6 and 7, we took a look at an overview of all the planets within our solar system. So now we want to piece this together and see if we can't come up with a model, a theory for the origin of the solar system. So we'll go ahead and get started in here. So it is our home in the universe. The solar system is our home. So we have the right and the responsibility maybe to even wonder about what we are. And so the whole summaries of throughout the book have been what are we sort of things. But our kind, meaning humankind, have inhabited this solar system for at least 1 million years, which is really just a blink in the eye of the universe, right? Or even our solar system. But within just the last 100 years have we even just started to begin understanding what the solar system is, let alone what the universe is as well. So we're still kind of new at this, but the amount of information that we've been able to learn and understand has been phenomenal. So we are linked through a great chain of origins that began that first instant when the universe began in the Big Bang, 13.7 billion years ago. If you remember that we refined that date to 13.7 billion years. And so the links in that chain is really one of the most exciting adventures of human intellect. We are thinkers, thinking beings. So now we study the origin of the universe in the Big Bang, that the subatomic particles of all the hydrogen and the helium that we see ever present in the universe even today began in those first few moments of the formation of the universe in the Big Bang. And then a little later, galaxies were able to form. The stars within those galaxies were able to cook up metals that were even heavier and spew those out. And then, of course, planets form around some of those stars. So the origin of the stars, production of the chemical elements in there. And here we're going to explore further and consider then the origin of our planets around our star. So the solar system, the history of the atoms in our body. And so like I mentioned before, the hydrogen, the oxygen that make up the water in our bodies even came from the subatomic particles in the Big Bang, right? The protons, the neutrons, the electrons in our bodies. about 3 minutes. When the universe was about 3 minutes old, we had those. So we are made of very old matter. That one that we are stardust kind of thing definitely does hold true. Most of that matter was hydrogen, like we mentioned, and about 25% of it was helium. But very few of those heavier ones were made at the Big Bang. Remember, those got cooked up in the stars, right? So those ancient hydrogen, though, atoms that we do have in our bodies, those originated unchanged as the universe kind of began, and then got recycled and recycled to create our solar system and to create us as well. So it's kind of taking you through that generation after the Big Bang, hundreds of millions of years after creating our galaxies containing billions of stars. So it's kind of going through that. Things like the carbon and the nitrogen and the oxygen, things that are common in our bodies, were assembled in those very massive stars, right? Most of the iron in our body. So as those massive stars died, right, the supernova explosions, conditions were just right for even heavier atoms, like the iron in our bodies. So carbon fusion in the type 1a supernova, decay of radioactive atoms expanding in the type 2 supernova, heavy metals like cobalt and iron, nickel, these types of metals forming in those explosions of stars, and so enriching the universe of heavier. And so these stars, of course, were created and enriched as we went along, and so our galaxy contains at least 100 billion stars, of which the sun is one of those. That formed about 5 billion years ago. We get that number from the stellar models, remembering sort of the ages of our stars by the turn-off points, right? We can estimate ages from stellar models. So for the sun, it's about 5 billion years ago. Of course, the atoms in our body were part of that star. Okay, and so this is taking you kind of through that history. And so a geologist by the name of Preston Cloud remarked that stars have died that we might live. And so that does ring true as well. We are stardust, right? So we are part of that great chain of origins that created the atoms, and then the stars, and then the planets, and then of course us as well. So astronomers have a theory of an origin of our solar system that's consistent with both observations of our solar system and observations of the formation of the stars. All that good information we're able to gather about that. So the solar nebula theory is what they have arrived at, and that's our best explanation of the origin of the solar system, and we call that the solar nebula theory. So it proposes that planets form in these rotating disks of gas and dust around our young stars, okay? And so we've seen some debris disks around some of our stars, even in the Orion Nebula, where we do see dense disks of gas and dust around young stars. And so these are sort of like prenatal planets around there. So we do see evidence of that to be pretty common around young stars. We can observe that today. So the idea is comprehensive, and it explains so many observations that it has graduated, if you would say here, from being just a hypothesis to being a theory now. And in science, the scientific theory has been really elevated and tested, and our best explanation going out there. So it's a theory, right? Okay. Yeah, and so like I'm mentioning here, these are some where there are debris disks around some hot young stars, and they're just kind of showing you this. We can image those disks directly. So here's sort of the proposal here that our own planetary system formed in such a disc shape cloud around the sun, and it all got to going in a circular orbit around the forming proto-sun. Okay, Earth and the other planets formed billions of years ago as the sun was condensing from that interstellar medium, as the stars, dense molecular clouds, and they get a shock wave that creates them to collapse inward. So our protosun was forming. And then all the gas and dust disk, kind of debris disk around it. And then you're seeing some little coagulation in there, forming planets around our growing baby sun in there. So planets should be very common in the universe, and we'll see towards the end that they have found some extrasolar planets around other stars, so it seems like it should be pretty common. So here we're going to begin with the most general view of the solar system. It's got a lot of empty space in between it. It's mostly empty space, honestly. Here they're trying to just kind of give you an analogy of a comparison of it. Say we take the sun and it's a small size of a small plum kind of thing, and we would put the Earth about 4 meters, so 4 meter sticks away from our plum, and the Earth there, and then the Jupiter would be about the size of an apple seed, about 20 meters away from the sun, and then Neptune's like way out there at the edge, and it'd be about 120 meters away, and it's just like a little large grain of sand, they're saying. So these, just to kind of give us a perspective on scale for that the planets are just little tiny specks around the sun. So most of the mass of the solar system is in the sun, okay, and that's the main part of it. So the planets do revolve around the sun, so they got in and began orbiting around because of the gravity pulling it and flattening that out into a disk shape, basically, as it rotated. Okay, it flattened out, and we kind of saw that hypothesis for our galaxies. As all the stars were orbiting the common center of mass, it also flattened out to a disc-like shape, like your blob of pizza dough as you rotate it, kind of thing. So the planets did that as well. So seems to kind of have all the same motion, although we did mention some exceptions with some of our moons in there, but it does appear as a common rotational theme that is counterclockwise. Rotational on their axis counterclockwise, and in their orbits, their revolutions around the sun. These all seem to be in a counterclockwise motion. So a common direction of rotation does seem to be seen around the sun. A commonality that a lot of them have, although Venus and Uranus, you remember Uranus, I didn't bring my little thing. It got knocked over on its side, right? Kind of thing. But Venus rotates backwards from the common theme, and Uranus rotates on its side, right? It got knocked over with its equator almost perpendicular to its orbit. But the main direction for most everything is in a counterclockwise fashion. Of course, that's seen from the north. So this seems to be related to the rotation of the solar nebula material around the sun that ended up becoming the planets in there. So planets, all the planets do revolve around the sun in that direction, and so those little exceptions in there, they rotate on their axes in the same direction, whether or not in their revolution kind of thing might be a little different. And they feel they've got some things worked out for explanations on those little exceptions. So most of those. So nearly all the moons in the solar system, including Earth's moon, orbit around their planets in a counterclockwise fashion. We did give you, an exception. I believe it was Triton. Triton, orbited in a retrograde motion. with respect to Neptune, if you remember that one. And we do feel like it did get knocked around a bit. So, yeah, that common revolution and rotation following a common theme within the solar system. So, seems like, that we're onto something there. And so, as you're looking here, two kinds of planets, which we just went through, Chapter 6, the terrestrial, Chapter 7, the Jovian, and we do see very distinct sets of planets. Although they're very unique in their own right, we do have two types of planets, the terrestrial or Earth-like, and the Jovian or Jupiter-like planets. So small, very dense Earth-like worlds, the terrestrial, or those giant, very large, very massive Jupiter-like worlds, the Jovian planets. So there's a distinction between the planets, and I did kind of allude to the fact that there was a condensation sequence, and depending on how far away you were from the sun, certain materials would condense out and coagulate and form solids at varying temperatures. And so that helps us set up a dividing line for the difference between our two planets, two kinds of planets in there. Okay, so that difference is so dramatic that we might say, aha, this must mean something. And so there's a couple, I think there were a couple pages in there, but the differences is one here, they're distinguished by their location. So the four inner planets, so Mercury, Venus, Earth, and Mars, the four inner, they're quite different from the outer. So then you have Jupiter, Saturn, Uranus, and Neptune, right? The outer ones, quite different, okay? Almost every solid surface in the solar system, as we saw, was covered in craters or had craters at one point. Maybe they resurfaced their surfaces, slow surface evolution, but nearly everything had craters on it. Okay, so that was something common to think about. Why did everything have craters on it? And the planets are distinguished by some individual properties such as rings, clouds, so the weather, in their atmospheres, and their moons. Most of them had moons. A lot of the terrestrials do not have them because they're much smaller. But of course, our theory, our solar nebula theory, needs to explain those properties. Okay, why some of them had ring systems, extensive satellite systems, but the other ones don't. So we need to make sure that our theory does touch upon that. So the division of the planets into two families does give us clues about how the solar system formed. So further clues that we can look at are what we call these smaller objects that have remained largely unchanged since their formation, on the order of 4.6 billion with a B, billion years ago. These would be things like meteorites. So anytime we can get some space debris down here on our planet to get a look at, these have gone unchanged since their formation, since the birth of the solar system. So these things, these space debris, asteroids, which are leftover kind of rocky bodies that didn't get incorporated into a planet, comets, the icy bodies, so those icy planetesimals way out there, didn't get incorporated into some of our ice giants out there. So, and then the meteoroids. So these are little debris that are near our atmosphere. Some of them actually do enter our atmosphere. A lot of them will get burned up. Some of them do survive. The meteorites survive, and then we can study them. So these are just a tiny, tiny fraction of the mass of the system, but they give us some tremendous amount of information about the origin of our planets. Okay, so they're going to talk about some of the space debris, the asteroids, sometimes called minor planets, but these are rocky worlds. So most of them interestingly enough, they orbit the sun in a belt between Mars and Jupiter, right? So Mars is the farthest out of the terrestrial planets, and Jupiter's like the closest in of the Jovian planets. So right in between. Mars is about 1.5 AU out, Jupiter's about 5 AU out. So right in there, in between, at what we said about 3 AU from the sun, is this asteroid belt. All this rocky debris, okay, lying right in there in the asteroid belt. So you probably can't see that too well, but out in there. And so they can occasionally collide with some of the planets, and of course Earth has been struck many times, but this is, their hypothesis on this is that a planet was trying to form in that region between Mars and Jupiter, but because Jupiter was so massive, the gravitational influence of Jupiter didn't allow the planet to actually form, to accrete, condense and accrete and become a planet. So we have all that debris out in there. This rocky in nature, similar to our terrestrial planets. So, you know, they're just kind of talking about, you know, sizes and 10 kilometers in diameter. Some are a little more larger than that, but our telescopes can't quite like get real good details, but some spacecraft have gone to them and been able to get really, even land on some of them, amazingly. But they're very cratered, okay, and battered up from the impact cratering that occurred. Like about everything in the solar system did get battered. So these are just some examples of them. They're kind of oddly shaped, broken. They're not real spherical. They weren't able to really pull themselves into spheroids. But multiple collisions of the asteroid sort of thing. So these just didn't come together as a planet as the planets were forming. And so collisions between the planets knocking the debris and forming all of this rocky material out there. These are our asteroids, right? And they are saying that there was a planet that failed to form at 3 AU. And so leaving behind this sort of belt of construction material they're referring to there. The comets, so some more rocky, or not rocky, but space debris. These are the icy bodies. So comets are icy. And the brightest comets, really as they get closer into the sun, will have these gorgeous gas tails and a dust tail only as they get closer into the sun. And they have, you know, some pretty elliptical orbits. So most of the time they're really far away from the sun, and then they get a little closer to the sun. And when they do get closer to the sun, that does create the ionization of the gas, and it glows brightly, and we can see some of these. Maybe you need a little binocular or something to see them, but they are some of the most impressively beautiful objects. So, but these are coming from way out there in the outskirts beyond Neptune's orbit, even out there where the icy bodies, the dwarf planets of Pluto reside, in that place that we mentioned, the Kuiper Belt. And that's onwards at about 50 AU from the sun in the Kuiper Belt. But the icy planetesimals out there that, you know, did not coagulate into a planet. So some space debris of comets out there. And so I think they're going to talk about, you know, coming closer to the sun, and then we'll give you those beautiful bright tails. And so we have ices of water, carbon dioxide, methane, and ammonia ices that are in our comets. It's sort of the recipe in a comet, various kinds of ices out there, which is pretty common of what we're seeing in our outer planets, because that's the material that's able to condense that far away from the sun, so those ices make good sense. And so they are coming from way out there in the solar system. Okay, and they're just kind of showing you some of the gas and dust spewing as it got closer to the sun. So they're just showing you a few examples of that. Okay, and they're mentioning the term Kuiper Belt. So named after the Dutch-American astronomer Gerard Kuiper, who predicted the existence of these objects back in 1950. And there are probably 100 million bodies larger than at least 1 kilometer out there in the Kuiper Belt. And so, of course, our nebula theory needs to be able to explain why we're seeing those icy bodies out there. And so they have short orbital periods or long kind of orbital periods. The ones with short orbital periods, they do think are coming from the Kuiper Belt. And even further out from the Kuiper Belt, we have something called the Oort cloud. And it has icy bodies, but they feel that those are the long orbit comets coming from way, way out there in the Oort cloud, a little further out even. So meteors, so back to kind of meteors flashing across the sky. We mistakenly call some of those shooting stars. Stars don't get into our atmosphere, right? No, our nearest star is 4 light years away. So these aren't stars. We mistakenly call them shooting stars, but it's a streak of light, meteors flashing through our atmosphere. It's actually bits of rock and metal that are burning up because of the friction as it's entering our atmosphere. Occasionally, so those are called meteors, like a meteor shower sort of thing. But if it actually makes it to the ground, if the piece makes it to the ground, it's called a meteorite, okay? The meteoroids, so it's a meteoroid, a meteor, and a meteorite, a lot of M words there, but a meteoroid is when it's in space just before it enters the atmosphere, okay? Before its fiery plunge kind of thing. It's called a meteoroid. So out there in space, it's called a meteoroid. As it burns up and kind of goes through our atmosphere, that's a meteor. And if it actually does make it to the surface of the Earth, it's called a meteorite. So let's try to make sure you got those terms clear, okay? Yeah. And there are some categories of meteorites. So can be divided in some broad categories. So an iron or a metal, a lot of times it's iron and nickel in the meteorite. Stony would mean that it's more silicate or rocky, like our rock material, the silicates. And it could be a combination of stony and iron. I happen to have a sample of a stony iron one here. I'll try to pop it under the screen. We'll see. This is a sample that came from Kansas. It's a nickel and iron, and it does have some chondrules of some silicate material, rocky type material. Let's see if that'll make it any better or worse, but sort of the pieces right in there are the iron kind of nickel alloy combo, and then these darker ones are the stony material. So this would be like a stony iron example of a fall that they found out in Kansas. Brenham, Kansas is where this one was found. So a meteorite example. So anytime we can get our hands on a meteorite, that gives us a direct study of the early formation of our solar system. So we are very excited when we can find those. It survives its passage. So here they have some more examples of that. The one I was showing you was like a stony iron combination one, the mixture of the iron and the rocks. And this one, a metal one, so an iron one. And this one is tended to have a fusion crust on it because as it's coming through our atmosphere, things are really heating up. So it tends to get sort of a fusion crust from the melting as it enters Earth's atmosphere with these. So can be a combination of silicate and iron in those, pure iron, or the silicate in there. Those chondrules or chondrites, so they're saying a chemical composition that resembles a cool lump of the sun with hydrogen and helium removed, right? The volatile parts of it removed. So they really do give us some good information about the early kind of formation of our solar system. So we love to get a hold of our meteorites. So, and then maybe you've experienced the beautiful meteor showers, and so you can watch a display of that. So as we're kind of in our orbit going through our revolution around the sun, sometimes we get into this debris and we're moving right through it. So a lot of times it's very predicted that we will know when we're going to have a meteor shower. Off in a direction of a certain constellation, they'll say, the Lineads, the Perseid meteor showers. So they can be predicted because that debris is out there, and then when we finally in our orbit go through it, we can kind of predict that, oh, you're going to see a wonderful meteor shower tonight, sort of thing. So we can predict some of that. Yeah, so here you have, say, a comet leaving behind all its debris, and then the Earth happens to go right through some of that material, some through that debris, and so we can have a nice meteor shower in that. So the Perseus, they talk about Perseid meteor showers in August, sort of thing. So it can be kind of predictable on this. So meteorites are very important to mention here, is because the clues that they can give us concerning the solar system. The meteorites can reveal the age of the solar system. So we've age dated our meteorites, and they're very consistent with being about 4.6 billion years. And so we have a lot of agreement in the age of the Earth rocks, the age of the moon rocks, things that they believe are from Mars, the ages of those, and these meteorites, space debris that makes its way to our Earth's surface. And so they can study all that and have a common age of the solar system objects. In addition and separately from that would be stellar models about the sun being about 5 billion years old, plus or minus about a million or a billion and a half in there. So it really is an extra good way when we can get a hold of those to kind of cinch our ideas, our thoughts that, hey, what's the age of the solar system? And this just really helps us with that. Okay, so they're talking about, well, how can you get the age of rocks and that sort of thing? And so rocks even here on our planet are made up of some radioactive isotopes, we call them, which are variations of normal elements that happen to have a little variation in their nucleus. So an element has all the same number of protons. That's what makes a particular element a particular element, is the number of protons in their nucleus. But what can vary is the number of neutrons in the nucleus. And so isotopes are variations of elements that have a little bit different number of neutrons in the nucleus. Some of these isotopes can be radioactive. They are unstable, and so they will spontaneously decay. So that's known as radioactivity. They will spontaneously decay down into stable daughter products, okay? A stable product, okay? They call that a daughter isotope, okay? A daughter product in there. And they will decay at a specific rate. So we have many, many different kinds of isotopes, radioactive isotopes, and each one has a unique amount of time that it does decay. And so we call this a half-life, okay? The half-life of a radioactive element is the time that it takes for half of that radioactive isotope to decay into the stable daughter products. Okay, however much time that is, that will depend on what radioactive isotope you're dealing with. So we can look then, we would measure the amount of radioactive atoms to the ratio of the stable daughter product atoms, get a ratio worked out. You can take these samples into a lab and get that spectral analysis and atomic spectral analysis and get your ratios, okay? And so from those ratios, combine that with having an understanding of what the half-life is, we can calculate the age of many of our rocks. And so here's a little diagram that's showing the percentage of the remaining isotope versus the age in half-lives, okay? So remember, one half-life is the amount of time that has to go by for half of the parent radioactive isotope to decay into half of the daughter, stable daughter product. Half and half, 50% and 50%. That's when one half-life has gone by, whatever that age is for your isotope. Okay, so in our first sample here, I hope you can see the colors on here. The red little dots is indicating a radioactive isotope. And we have 100% of that right now, radioactive isotope. After one half-life has gone by, that was time enough for half of those parent radioactive isotopes to, through a series of steps, decay into 50% of the stable daughter product. So the blue dots on here are the daughter products. And so 50-50, okay? 50-50, 50 parent, 50 daughter, okay? And one half-life had gone by. So if you analyzed your sample and you saw that ratio, parent to daughter, 50-50, you knew one half-life had gone by. Well, let's say we get a sample where we're seeing 1/4 of the parent remaining. So each successive half-life that goes by, you are having the parent, the remaining parent isotope in half, okay? So now we only have 25% of the parent and 75% of the daughter. So if you saw a ratio like that, 25% radioactive isotope to 75% stable daughter product, you know, 2 half-lives went by, okay? And if we did another third half-life go by, we would see only 1/8 of our parent remaining, okay? And the other would be, the rest here would be daughter product. So you're looking at ratios and being able to tell how many half-lives have gone by, okay? And you can assign an age, a numerical age to this. So there are many, they're talking about many radioactive isotopes. You know, we think of uranium, yeah, that's one that we actually like to use. But calcium and argon, there's many of them that could be used. And so as the time passes, the abundance of the radioactive element gradually decreases, and the abundance of the daughter product increases over time. So we can age date our rocks in this manner. The ones here on Earth, the lunar rocks that we got from the moon, and things that they are certain came from Mars, and any meteorite that we happen to get, space debris, we can do this. And so we can find the radioactive age of our samples in the lab. We can do that. So things like Earth rocks, the moon rocks, Mars, some that they're sure come from Mars, and meteorites. This can be done. It's amazing. And our technology really only came about for this in the 1950s. So, you know, pretty new technology that we have here. Okay, so the age here of some of the oldest rocks on Earth coming from Australia have been age dated to 4.4 billion years old. So we could say that, you know, at least Earth is at least 4.4 billion years old, right? But again, you know how we have plate tectonics, and some of our crustal rocks are getting recycled, sort of thing. But at least 4.4 billion years old by using radioactive decay measurements on that. Okay. Let's see, the moon's surface, okay, is not being recycled geologically, right? It's a geologically dead surface. And so the oldest lunar rocks that were brought back by the Apollo astronauts were age dated at 4.48 billion years old, which is in good agreement with our Earth rocks, right? So it means the moon must be at least 4.48 billion years old, so almost 4.5 billion. So these are some good data that we can collect for this. And then some things that they're sure that came from Mars, meteorites that they found. They've been age dated to 4.5 billion years old. And so, again, we have a common theme for some of the ages of our rocks in a few places. On Earth, the moon, and Mars anyway. You know, the ranges of those age are pretty consistent with being about 4.56 billion years old. And so really, if we put the model of the sun, the stellar models in with that, so widely accepted age of the solar system gets rounded up to 4.6 billion, with a B, years old for the solar system. Okay. Often rounded to 4.6. And in agreement with the age of the sun, which was, you know, roughly 5 billion, but plus or minus 1.5 billion, they say. So it's really in good agreement that all the bodies in the solar system formed at about the same time, 4.6 billion years old. So radiometric age dating, you need both that information of the radioactive element, isotope, and the stable daughter product. That information together with the value of your half-life for your particular isotope, combine all that, we can get some radiometrically aged rocks out of that. So that's some good data that we can use. Okay. The chemical composition of the solar nebula. So what is the composition of the sun? So we've got a cloud, you know, forming out of mostly hydrogen, mostly helium, right? And so we can look at the spectra and kind of get a gauge, and it had, you know, some other elements in there as well. Some of the nuclear reactions are fusing the hydrogen to form even more helium in there. So we're getting, you know, a few heavier elements kind of getting cooked up in the core, right, as the star is living. And so we do see that same kind of solar nebula composition reflected in our planets, right? So the sun's forming out of this dense molecular cloud with all sorts of materials in it, and our planets are forming from that around there. So position away from the sun really helps us understand the composition of our two planets, right? Our terrestrial versus our Jovian. So the low density gases, right, if they are volatile and kind of escape off, we would kind of see the composition of what the terrestrial planets would be. The silicate and kind of the rocky and the metallic type of material. Because they're small, they can't really maintain or keep a hold of that gas, like the hydrogens in there and some of the other gases. So that would make good sense that those would be the ones would be the rocky and the metallic ones, kind of closer in. And they're talking about an uncompressed density here. So the densities that the planets would have if gravity didn't compress them can be calculated from the actual densities and the masses of each planet. And so the ones that would have sort of the highest uncompressed densities would be those terrestrial planets, the ones closest in, the ones that were rocky and metallic in there. So definitely the uncompressed densities would be greatest for those planets that were closest in to the sun. So your terrestrial planets in there. And then very low density are gas giants further out, away from the sun. So the closer a planet is to the sun, of course, the higher its uncompressed density would be. So the inner region of the temperature of the nebula was probably around 1500 Kelvin. And so those types of materials that would condense out, think of our condensation sequence, I'm sure they're going to pop it up here in a second, would be where the metals, right? So the metallic mercury would be the one closest into the sun, and so it makes great sense that it is a metallic, pretty much a metallic planet. It's got a little bit of a low density crust around it, but are things with high melting points like the metal oxides and the pure metals. So these are very dense, and that is the composition of mercury, if you recall that. So yeah, our rocky material a little further out, and our metals, that's what our terrestrial planets are composed of. Makes good sense because of their position from the sun. Farther out, okay, we're able to get, our silicates or our rocky material. So Venus, Earth, and Mars definitely has that in it. And even a little further out, there's a boundary that they called an ice line, in bold there, where water vapor could freeze and become ice. And we do see many ices, the methane ice, the carbon dioxide ice, right? So where things could now, even ammonia ice, that could freeze out there. So you got far enough away from your sun that you could get many kinds of ices to form. Water vapor, methane, ammonia would have been abundant in the solar nebula. So beyond that ice line, there's just like this blizzard of ices swirling around, and those ices have a low density like our Jovian planets do have. Remember how we said even Uranus and Neptune should be called the ice giants? So our Jovian planets, Jupiter-like planets, have the lower densities, which is consistent from their position away from the sun, what the temperatures would have been like. Here's that condensation sequence, and it actually should be table 8.2 because this is chapter 8. They did a little revision, and these are old PowerPoints. So, but that is known as a condensation sequence that we talked about. A sequence of how these different materials would have condensed out of our solar nebula around the sun. And it seems like temperature is the key to this. So where is your position? How far away are you from the sun? That's going to dictate your temperature, right? And so we showed you this back in chapter 6, I think. We had it up here briefly, but yeah. So at 1500 Kelvin, that's where the metal oxides, so something like mercury, would form there. That's what we see in the composition of mercury. And you're getting a little cooler temperatures, you're getting the iron and the nickel. 1200, you're getting the silicates, which are silicon and oxygen. Very much what our earth materials are made of. Feldspars at about 1000. So your feldspars are also a variety of silicate material as well. Venus, Earth as well, has that. Something like iron sulfide, triolite. The Earth and Mars has that in it, so iron and sulfide. Getting way out here now, where we can get water ice, we can get ammonia ice, right? So NH3, methane, CH4, argon and neon, some of our noble gases become ices. And so your Jovian planets, okay, much lower temperatures here. And they're even mentioning Pluto way out here. So this is a condensation sequence that makes fantastic sense. This is in table form. I actually have something that maybe will help you with this. Just kind of a color coding little diagram I found that might help you see this in just a slightly different way rather than a table format. This might help you as well. So in the center we have the proto-sun, our little baby sun forming, right? And then the nebula around that. And so as you go away from the sun, of course the temperature gets cooler. 2000 Kelvin, 300 Kelvin, 50 Kelvin, and they got it color coded, right? The cooler temperatures are the blues, right? The hotter ones are the reds and the oranges in there, kind of like what we saw with the stars. And then on the other side, they're showing the type of material that would condense out at those temperatures. So metal and rock, a little further out, water, ice, and even further out, we got carbon dioxide, the methane, and the nitrogen ices. So things that we think of as gases here on our planet now can become solids, these ices. So just another little way to look at that condensation sequence. Took in a table format and kind of a color-coded. Same data, but just showing you it in a slightly different way sometimes can be helpful. So hopefully that was. Okay, so the condensation sequence really does help us get a grip on why we do see the differences of composition in our planets as you go out farther from the sun. And so temperature is your factor of that, okay? And the ice line seems to be somewhere in between Mars and Jupiter, okay? And that is where the separation of the very dense inner terrestrial planets get separated from the low density Jovian planets. So that is a very good piece of our solar nebula theory, is the condensation sequence of solids. And so that one does make very good sense for us. Really enhances our solar nebula theory. So the formation of what we call planetesimals. So how did all this dense sort of debris disk end up forming the solid particles and then the planets eventually? So there's three groups of processes that operate in order to collect little solid bits of matter, the rock, the metal, or the ices, and create larger bodies we call planetesimals. Okay, the planetesimals. So eventually these planetesimals are going to kind of coalesce and create the planets. And so some of the processes that they talk about, first one here is the condensation, second one accretion, and then for very large ones we can get gravitational collapse. When they get massive enough, like our Jovian planets, they can just by gravitational collapse because they become so massive. So these are the three processes of the formation of our planetesimals, okay? And they're going to take us through this. And so condensation is when you are adding matter or material one atom at a time, one atom or molecule at a time, from the surrounding gas. So one atom, molecule at a time, you are adding, okay? That's called condensation, all right? That's basically your first step. So you're gonna start to get little bits and particles there, little flakes in the solar system by that process of condensation. That's the first step, okay? Then, as our little solar nebula is getting these little flakes and grains of dust kind of thing in there, the little atoms of gas are kind of getting stuck to them, okay? And so they'll begin to accrete. That's kind of the next one. So the sticking together of solid particles is known as accretion. So the sticking together of solid particles to produce an even larger particle. Now, when your diameter gets greater than a kilometer, they call that a planetesimal, okay? So kind of a size thing for that. But the actual sticking together is called accretion, okay? So there's really no clear distinction between a very large grain and a very small planetesimal, but we try to go with that number of about 1 kilometer, and we're calling that object a planetesimal at that point, okay? So kind of a growing from collisions of the surrounding gas around it, and then accreting little flakes of that, and creating a planetesimal, okay, from a condensation and then accretion, okay. Now, when you get the coalescence of your planetesimals, so again, over a kilometer in size, you can get the coalescence of planetesimals, and then that's going to form what we call a protoplanet. Not quite a planet yet, but we call it a protoplanet. Okay, so the coalescing of planetesimals will form a protoplanet, a massive object destined to become a planet if everything goes well for it. So let me just write that series up again for us, kind of how the process goes. So condensation, and accretion forms a planetesimal. And the coalescence of planetesimals forms a protoplanet. Okay. And so when your protoplanets gets, a little over 15 Earth masses, then that other term we talked about, the gravitational collapse, can occur. And so that would be something that the Jovian planets would have used, would be in the gravitational collapse in there. So our planetesimals are all kind of moving in the same direction, orbiting around the sun. So they didn't really collide head on, which that velocity would have probably, evaporated them. They were all kind of going in the same direction, so they were just kind of, rubbing shoulders or kind of bumping together like that. And so that they could kind of accumulate and stick together kind of thing and coalesce. So if they had been going all in different directions like that, they really would have probably annihilated one another. So protoplanet growing and coalescing and getting larger and larger and creating these little baby protoplanets. And so once our protoplanet approached 15 Earth masses, so the mass of Earth, but times 15 times that, so we're really talking about Jovian planets at this point. These could grow and accumulate matter by gravitational collapse, because now they're massive enough that you can get a very rapid accumulation of the large amounts of infalling gas. So they could pull in gases now, which is our gas giants, right? Our Jovian planets. And so greater than 15 Earth masses we could get growth through gravitational collapse. After that. Okay, so sort of a process in there. So condensation and accretion, coalescence of your planetesimals, and then for the even larger ones, gravitational collapse once you got massive enough. And they would get very, very hot from that, from all that infalling gas and speeding rapidly coming in there. These would have gotten really, really hot, our massive planets in there. So yeah, the rapid accumulation of infalling gas, our protoplanets of the Jovian planets could have grown very hot from that infalling gas rapidly falling in, creating at a very high velocity. So these could have gotten very, very hot by that. Okay. So So this is just going to take you through the series of kind of how that terrestrial protoplanet would have grown. So here we have some little, condensation, then accretion, getting our little planetesimals, and so those little planetesimals begin to kind of coalesce in there. And so as they are coalescing, our planetesimals, they're completely homogeneous in their composition, completely uniform and homogeneous in their composition, and they're just coalescing into a sphere, okay, but completely homogeneous, right? So we talked about how the Earth and the other planets kind of have this differentiation, most dense of material towards the center, kind of medium density, and then least dense on their outer parts of the surface there. These were completely homogeneous, our little planetesimals. So now how'd that differentiation happen? And so they're going to kind of take us through this, I believe. So as they are kind of coagulating together, coalescing together, this is eventually going to cause the heat to accumulate in the interior, and the decay of some of that short-lived radioactive isotopes creating heat from that would eventually have melted the planet entirely, completely molten material. So it has to become molten, melted the planet altogether, that then as it began to cool once again would have allowed, right, that differentiation, the separation of the material according to its density. So the rocky material, right, is less dense. The very heavy metals, so the iron and the nickel cores, those metallic cores, that material would have sunk to the center, so creating the heavy kind of metallic cores that we do see in our planets, including Earth. And then the least kind of rocky material would have been less dense, and that would have floated to the outer parts, so creating then that silicate kind of less dense rocky crust. Okay, so this is sort of how the differentiation into the layers, like we studied with Earth in particular, but the other terrestrial planets do show that, and even our Jovian planets do have a semblance of the metallic cores in them, and then of course they're less dense with a lot of their gases. But the differentiation, right? The lighter silicates will float to the surface and form that low density crust, and the heavier materials, the metals, would, like iron and nickel, would have settled in the core. Okay, and so this is the idea that they were condensing and accreting and making planetesimals, and those little coalescence rubbing shoulders of the planetesimals, creating a little protoplanet, and then the radioactive isotopes would have heated it up enough so the heat of formation, sometimes we call that, would have melted that material entirely and allowed it to differentiate by density. And so that's sort of a process that very well explains the layering of our planets. So good evidence there that does make good sense for our layering. And here they're talking just a quick thing about so planets are formed and later melted by radioactive decay. That would have released a lot of gases from the planet's interior, and that could have formed that primary kind of atmosphere if they were kind of massive enough to hang on to their atmosphere. So the creation of a planetary atmosphere from the planet's interior, so the outgassing from rock material, that's known as outgassing, and forming some of that early on atmosphere. That's known as outgassing. Okay. So our little planetesimals, maybe didn't have a lot of, like for the formation of Earth, that maybe in their neighborhood it wouldn't have had a lot of water. So how come we're the water planet? What happened there? So we think that the Earth's water probably formed a little later in the planet's formation, in which of course there was a whole blizzard of things going on out there, where Earth was able to kind of sweep up some volatile rich planetesimals that were forming as the nebula continued to kind of cool. So some icy planetesimals, they may have formed farther out, but then kind of got scattered around because our big guys, our Jovian planets, were forming. We also talked about how Uranus and Neptune probably formed closer in to where Jupiter and Saturn were, so that would have knocked a lot of the icy bodies around, could have flung some of that, those planetesimals towards the terrestrial planet. So they're thinking, you know, those icy planetesimals could have got scattered around, and we swept some of those up and got a lot of our water in that manner. Okay, so I think they got that one figured out as well. Yeah, so yeah, I was trying to think that how the very massive ones began to do by gravitational collapse, and sometimes they do talk about that might be the Jovian problem, I think they talk about in here. Let me see if I can find that. Well, this is just further evidence of the bombardment. So kind of the planetesimals coalescing, well, that we're still getting hit. The planets are still getting hit and coalescing, so to speak. And so here is Meteor Crater out there in Flagstaff, Arizona. It was like one of the first verified meteorite, you know, craters here on Earth. And it actually, that kind of looks like me over there. I'm seeing the frou-frou hair. You probably can't see that very well. I actually did stand out there. That one's not me. But I did stand on that ridge and look out at Meteor Crater. But this one is the first confirmed here on Earth that was an actual formed from a crater or from a meteorite. And they have a museum there, and this is just a piece, just a tiny fragment of, there's the gentleman that talks about it and takes you on the tour of this, but Meteor Crater, the best preserved and first proven meteor crater on Earth, and this is a piece of it, the Barringer meteorite, just a fragment of it. I mean, it was much larger than that. This happened probably 50,000 years ago, so it's a recent event. So these bombardments do still happen, and so we are still kind of accreting, you know, planetesimals, right? So planets can get hit. I know they've seen Jupiter get struck by things as well. So yeah, meteorites hit Earth, you know, every day, but usually they're very, very small, right, to not cause any kind of a problem. So here's the one, 150 known meteorites, but that's the meteor crater out there in Arizona, Flagstaff, Arizona. So that's sort of the accreting kind of story. Continuing bombardment. Of course, all those things out there, all our little planetesimals out, they're going to bump into each other, right? And so we are seeing the cratering. Earth's moon, we looked at the Mercury, very cratered. Venus does, but it's kind of smoothed out some of its surface evolution, right? Mars as well, so they've kind of smoothed some of that out, but everything's cratered. Asteroids have craters on them, so there was this just kind of blizzard of things bumping into each other, impacting each other, and we call that the heavy bombardment period, which I've alluded to many, many times. So the craters seem to have been formed roughly 4 billion years ago, so early on in the solar nebula's formation. That was the heavy bombardment period. And then we often talk about 65 million years ago, during kind of towards the end of the Cretaceous period, a period in geologic time, where we had a mass extinction happen. And we always think of the dinosaurs dying, but it was a mass extinction, not just the dinosaurs. 75% of all the species on the planet went extinct at this time. That we do believe now, and lots of confirmation, that this was because of a meteorite, a very large meteorite that hit the Earth and put up a plume of dust and gas and, you know, blocked out the sun for an extended period of time. That spelled a lot of trouble for a lot of the organisms on our planet. So, and they have found some parts of this in Mexico, and so of the meteorites. So, yeah, Chicxulub crater in the Yucatan Peninsula of Mexico, and so. Yeah, some good evidence that, yeah, we've been hit before. And it, you know, we're continuing to, but it's an extremely much slower rate that these types of things are happening. Okay, so continuing bombardment. This was the one, Shoemaker-Levy 9, a comet slammed into Jupiter. Okay, so yeah, things are out there still, right? We still have some space debris out there, but not on the order that it was when the planets were forming, right? So, less often, right? And we're a little smaller too, so, you know, it has to be lined up just right to hit us. But we are sitting ducks. We are out there, and things are, you know, still moving around out there, planetesimals, asteroids and comets and things. So yeah, we're on the lookout for it. They are monitoring near Earth objects, you know, so maybe we can figure out, you know, to divert them somehow, if that's even at all possible. So they're talking about here about the Jovian problem. So the solar nebula theory has been very successful so far explaining the formation of our solar system, but here it's saying a problem here about the Jovian planets being the troublemakers. They're saying that the gas and the dust disks around the newborn stars shouldn't last that long, okay? Not long enough to get an extremely massive planet like, say, Jupiter, sort of thing. So their idea on this is that they could modify just a little bit to where our Jovian planets may have become very massive very quickly by the gravitational collapse, to the point that they could have skipped that condensation and accretion of a heavy core, and maybe just skipped that step altogether, and then became, you know, more massive, things sunk to the core kind of thing, and just skip that accretion of a, you know, a heavy core in the center there. So they run all their models to try to kind of explain that, so that if they can modify that just a little bit, they think they've got a handle on that. So you know, they could have formed quickly before the solar nebula disappeared, and without forming that dense core by accretion first. So if they could kind of skip that stage, they think they've got that handle on that. It also gives us some idea about Uranus and Neptune, right? So that the fact that they probably formed closer in to the position where Jupiter and Saturn were, and then migrated outwards. So that could help solve a lot of that problem as well. They're so far from the sun that accretion couldn't have built them up very quickly, but if they could have skipped that stage as well and then migrated out. And we do have all of those strange little, you know, exceptions. Uranus is kind of tipped over, and Triton is kind of retrograde with Neptune's moon. So they have some things that are problematic, but they don't think they're too problematic that it would say you have to get rid of the theory altogether, sort of thing. So the traditional one of planets accreting a core, and then if they became massive enough by gravitational collapse of a nebular, of the nebula gas, infalling like that, some of those outer planets could have skipped that accretionary phase and became very massive through gravitational collapse. Skipped the core accretion phase, and they feel like they got a handle on it. So, yeah, the little problem children of the Jovian planets. So, okay, so we've got here a table. I believe it's table 8.1 in your book. I think I've got it where I could get it enlarged here. It's kind of small on the screen there. So we want to kind of take a look at that and see how we're doing. This would be table 8.1. Characteristic properties of the solar system. Kind of seeing how we're doing here. And so they're saying the disk shape of the solar system. Yeah, so this does help us with the orbits of all of our planets. Even our, asteroid belts and our comets all follow the same kind of theme, but we have orbits in nearly the same plane towards the disk region of when that massive sun, baby sun, was forming, and a common direction of rotation on their axis and revolution around the sun. So the disk shape of the solar system is very nicely explained by the solar nebula theory. The two planetary types, and so it explains nicely the differences that we see in the compositions of our terrestrial inner planets. Those are very dense, right? They have high density. The condensation sequence, that's where our metals and our rocky material would come out at those higher temperatures. And our Jovian outer planets being very low density. So this is where the gases, the hydrogen, and the ices would be forming farther out. So good so far, it's explaining that very well. The planetary rings and the large satellite systems. So Jupiter, Saturn, Uranus, and Neptune, yes, they have the planetary rings. They all have them. Remember, some of them are harder to see, but they all have them, and they have a lot of large satellite systems. They're very massive, and so any little space debris that's out there that gets too close could get captured into their moon system. But no for the terrestrial planets, so Mercury, Venus, Earth, Mars. Now, no ring systems for any of them, but Earth has one moon, and you remember Mars had two moons. So the inner ones, there's no way. That's too close to the sun. The moons would not be able to stay put that close in. So that makes good sense of why we're seeing, and then the moons were the reason they had the rings, right? That we see that difference. The space debris, it explains the space debris quite nicely because, right, condensation, accretion, we're getting planetesimals, right? Some of those planetesimals eventually became planets, but there's a lot of leftover material. The heavy bombardment is good evidence that there was leftover material crashing into each other. And so our compositions of our asteroids and our comets make sense of where we're finding them in the solar system. The asteroid belt is very rocky material, right? It's in the inner solar system. Makes sense it formed there because that's where the rocky material is. Composition like the terrestrial planets. The comets are coming from way out there in the Kuiper belt, and some of you are even further out in the Oort cloud. Icy bodies, right? Our comets are our icy bodies, so composition like our Jovian planets, way out there in the solar system. So that's a good explanation there. And so this debris that's kind of left over, it just did not form into a planet. It didn't accrete and coalesce. So it did not become a planet, and it sort of bumped and knocked into kind of the other planets, collisions with the other planets, and sort of leftover debris explains our asteroids and our comets in there. And then the common age of about 4.6 billion years of our Earth rocks, the moon rocks that we brought back, Apollo brought back, the meteorites that there are certain came from Mars, and then the sun, the stellar models of the sun, putting that age of about 4.6 billion years, so a commonality of that. Yeah, our solar nebula theory has done very, very well to help us understand our solar nebula theory. So that's sort of a summary of the characteristic properties. I also made out a handout of some of that, so I'll try to make sure to get you a copy or post that on Blackboard so that you can get a summary of that. But this is a nice summary as well in your book, would be table 8.1 out of your book. A nice summary on how our solar nebula theory has done a very nice job in the explanation of this. Okay. So yeah, and then kind of explaining that the orbits of the planets lie in the same plane because that's where they were in the rotating, swirling around the solar nebula, and it collapsed into that disk. Okay, so kind of an evolutionary type of sequence of events, a theory for that. Okay, now there were a couple exceptions, right? Uranus is like tipped over, knocked on its side. Venus rotated backwards. So peculiarities could have been caused by impacts of some of the more massive planetesimals. They were getting battered around out there, and that was clear because of all the craters that we see. But yeah, so it could have catastrophically kind of knocked it off kilter, and even caused it to rotate backwards, right? But another one is saying possibly that how thick Venus's atmosphere is. We have all that carbon dioxide in there, that could have, because tides of that might even have reversed its rotation. So evolutionary theory versus a catastrophic kind of type theory, but details of that they're still trying to work out. But definitely there was lots of bombardment happening that could have knocked some things off center. The division of the planets, like we talked about, understood by the condensation sequence how far away you were from the sun, so temperature based on what was going to condense out, so that makes good sense for us. There's your condensation sequence again. So again, by temperature, position out from that, talking about how why we're seeing the differences that we're seeing on there. The heat of formation by infalling matter, of course, for our Jovian planets was tremendous, right? For these massive planets, and so they would have gotten very, very hot, but not hot enough to start nuclear fusion, right? Remember, Jupiter is one of those kind of brown dwarf varieties. They're very massive, but not massive enough to start nuclear fusion, right? Because that would have been the definition of a star. So Jupiter never generated its own energy, right? It's a planet, not a star. Okay. So Jupiter's still very hot inside. If you remember how we said Jupiter and even Saturn are radiating more heat than they actually bring in from the sun. So they're still cooling off from their heat of formation out there. And so this very kind of massive Jupiter was able to gravitationally disturb some of the nearby little planetesimals. And so remember how we said we kind of had that asteroid belt out there between Mars and Jupiter at about 3 AU out? Well, yeah, Jupiter is very massive, and its gravitational field can disturb some of those nearby planetesimals. And so that's why we see all that rocky debris that we do call our asteroids in an asteroid belt at 3 AU, right around there. So that helps. That makes great sense of why we're seeing it just couldn't make a planet because of Jupiter being out there. Okay. Let's see. And then in contrast, the comets, so our asteroids and now our comets, these are evidently the last of the icy planetesimals way out there with the ices. So some forming, you know, beyond the solar nebula, even beyond Neptune and Pluto. We call that the Oort cloud. So the Kuiper belt, and then the Oort cloud is even farther out. Yeah, so these ices condensed, and so we have some leftover kind of icy material we call our comets. Oh, here they're finally talking about the Oort cloud. So those massive Jovian planets could have ejected that icy material even further out to the far outer parts of the solar system, and that's called the Oort clouds. And they believe this is where the location of our very long period comets come from. So the short period ones are closer in the Kuiper belt, and then even further out we've got the long period comets. So these take a very long time to make their way around the sun, but that's in a region, kind of a shell region of the Oort cloud, they call that. So Kuiper belt objects, including Pluto, appear to be very ancient planetesimals. Again, Pluto is not considered one of our traditional planets anymore. It has a new class of the icy bodies called the dwarf planets, if you remember that. And so that's kind of the reason for the demotion. It didn't fit our, definition of a planet anymore. So, yeah, so these way out there probably haven't changed a whole lot. And now they're taking you through kind of the ring systems. Their large mass made it easier to kind of draw in little particles around them. They could capture objects as well. And so, again, the moons were supplying the material in the ring system. So our Jovian worlds do have the ring systems, the extensive ring systems. And our theory had no problem with the age, the common age of the objects that we see in our solar system. So they must have formed at basically the same age, roughly the same age in there. So it's done a very good job, and that's why it has graduated from a hypothesis to a theory, the solar nebula theory. It did a great job explaining those basic features that we do see in our solar system. So the origin of the solar system explained by the solar nebula theory. So look through your chart, and I had that little summary made up for you as well, and kind of think about those things and what we learned about all the various planets, and it does make good sense for that. So here, planets orbiting other stars. So if our star, the sun, has this elaborate, beautiful solar system, why wouldn't other stars have these? Now, if you think about it, if you remember back to our star unit, most of the stars, a lot of them, are in a binary pair with another star, a companion star. And as long as those two stars are maybe far enough from one another, they wouldn't intervene and disturb a solar system around another star. But if they're too close, they probably aren't going to be able to get a stable solar system around them. So our star doesn't have a companion, so there's no kind of interference as to why we would have gotten a nice solar system. But it would make sense that, other stars could have solar systems around them and planets forming around them. And so we've already seen about the dense disks of gas and dust around forming stars, right? And so the Orion Nebula we kind of talked about, that's a star forming region that's only a few million years old. And so, it probably doesn't have any planets just yet, because a few million years is really not a lot of time to get your planets together, but they have seen some with those disks of gas and dust around them that they're thinking we could probably be getting some protoplanets starting to form out there, and it should be pretty common around stars. These little sort of neonatal planets or prenatal kind of planets around stars, and so they set about to try to look at these and study these. And so here's one, Beta Pictoris, stars such as Vega in the constellation Beta Pictoris, that they are finding those kind of density of low kind of density of dust and gas around them, where there's a potential that we could get some planets to form around those debris disks that they talk about, and they have been detected, so that possibility. Now one of the first, let's find it, of an extrasolar planet was in the called 51 Pegasi, a star where they were able to detect some planets orbiting it. So that was sort of a very exciting thing, very important, because it's the first star like the sun that was found to have a planet orbiting it. So what they're kind of looking for are little tugs on the planet, or on the sun, because of the planets. As the planet's orbiting the sun, it's going to have a little gravitational effect on it, and so they're looking for those little wobbles in that gravitational field. So they're trying to show you here a lady trying to hold on to a dog, right? The dog's not leash trained at all, and he's kind of pulling her around. So she's wobbling a little bit, right, because of the gravitational field of her dog. Now let's say she has 3 unruly dogs and she's getting pulled all around because of her planets, her puppies going all around her. She's wobbling all around. So that's pretty much what they're doing. They're watching a star and seeing its motion, little gravitational wobble in there as the planet tugs on it, as it orbits it. And that's sort of the method that they use to try to detect planets that might be orbiting some of these other stars. And star 51 Pegasi was the first that they were successful. Planets are circling the star, and they're seeing that star wobble slightly from the spectrum, of course. And so they look at the little Doppler shifts in the star's spectrum. Remember how the spectra just revolutionized astronomy? Boy, did it ever. So those very small motions of the star are detectable in the Doppler shifts in the star's spectrum. And so that is how we kind of study to learn that, yeah, that one had some planets around it. So extrasolar planets, so from that motion. And they're thinking that these are estimated to be about 0.05 from their star, so not very far from their star, and that they're pretty massive. And in order to be able to detect them, that would make good sense that they would need to be something pretty massive to cause the wobble and to still be able to see it around the star that is pretty close in. So, and this just might be a selection effect. You remember we saw that with our stars and with our galaxies, because they're easier to detect. That might be. So, you know, that they're assuming that probably a lot of stars, many stars have planets around them, and so we need to kind of do further tests for this to confirm that. But since then, about 400 planets, and probably even more now, these PowerPoints are old, are being discovered around several stars in the Andromeda galaxy that we've looked at. And so, yeah, multiple planets around these. So this is one from Andromeda galaxy. So we would expect it to be fairly common with, you know, all the billions of stars that we do have out there. So Yeah, so, again, extrasolar planets can tell you something about the sizes of them depending on the tug of their star that they do. So lots of good research happening out there. But again, massive planets, because that's going to show you more of a gravitational kind of tug. Because our little low mass planets like Earth or some of those, they don't tug on their stars very much, and so you can't detect that very well. So it just might be a selection effect of why we're only observing the really massive planets around these stars. But we really shouldn't be surprised to expect some extrasolar planets around these other stars. So it seems like it might actually be a common kind of thing. But again, a single star, but most of those stars are in binary pairs. So yeah, so they're setting about to continue to find them. They are finding many of these orbiting stars, and so they've had some good success with extrasolar planets. So that's kind of concluding chapter 8. So make sure you go through all the bullets on your study guide, and if you have any questions, make sure to get with me on that. And so that really does conclude the astronomy course, and I have certainly enjoyed presenting the elements of astronomy to you. And I know we are all so busy in our ordinary daily lives, but I do encourage you to take a moment and look up and look out. The universe is all around you every day, and enjoy the cycles of the sky. You are very much a part of this very large and very beautiful universe. So I do wish you very well, and goodbye. Thank you.